Let's do a different sort of constant acceleration problem. This is one that, in some sense, is a little more real world. We have a proton traveling with a velocity of 5.45 times 10 to the fifth meters per second. That's actually a fairly slow speed for a single proton. It enters an electric field in which the proton accelerates at 2.33 times 10 to the 13th meters per second squared in the direction opposite its velocity. It's slowing down. Also, that acceleration, 2.33 times 10 to the 13th meters per second squared, is not unheard of and not that difficult to achieve with something like a proton. And the question is, how far will the proton travel before it comes to rest? This isn't too bad a problem. We can write down our constant acceleration equations. X equals x naught plus v naught t plus 1/2 at squared. That might help me solve it. That'll tell me how far x is given the initial velocity and the acceleration, but I don't know how long it takes to come to rest. I could get that from this equation. V equals v naught plus at. I could possibly solve this equation, set v equal to 0, and knowing a, I could figure out t. So that's a way I could do this. The givens that I have in this problem are that v naught is equal to 5.45 times 10 to the fifth meters per second, and the acceleration, because it's in the direction opposite the velocity, if I put a plus sign on the velocity, the acceleration will have a minus sign. So minus 2.33 times 10 to the 13th meters per second squared. So the way that I mentioned for doing this, there is a quicker way. Some of you may know this already, but if I take this equation right here and set v equal to 0, equals v naught plus at, that lets me figure out how long it takes for the proton to come to rest. In this case, I'd get t is equal to minus v naught over a. I'm working across the page here, which is a practice I don't like when you do your homework, but I'm trying to stay on the same sheet of paper here. Anyway, doing this, I would get minus 5.45 times 10 to the fifth meters per second. And on the bottom, I have the acceleration, which is minus 2.33 times 10 to the 13th meters per second squared. Now, minus on top, minus on the bottom, I'll get a positive time. Meters per second on top, meters per second squared on the bottom will leave me with seconds. Check those units out if you need to. And the time will be, I would get 2.34 times 10 to the minus 8th seconds. Another way of putting that is it's 23.4 nanoseconds. Okay, pretty short time, but not unheard of in a situation like this. Now that I know how long it takes to come to rest, I can figure out how far it will travel in that time. And I know V naught, I know A, I know T. I can let x naught equals 0. Just define where it is at time 0, or the instant it enters the electric field. Let that be the origin of my x coordinate. Then I would get x equals v naught t plus 1/2 at squared equals v naught is that 5.45 times 10 to the 5th meters per second. It's V naught times T, so I multiply that by the 2.34 times 10 to the minus 8 seconds, plus, we'll hope this fits, 1/2 times the acceleration, it might, 2.33 times 10 to the 13th meters per second squared, it won't, times, I'm going to have to fit the time down here, 2.34 times 10 to the minus 8 seconds, and that gets squared. Okay, plug in all those numbers and do the calculation. You may have noticed that I forgot to put the minus sign on the acceleration here when I was doing the calculation. What I get for that answer is 6.37 times 10 to the minus 3rd meters. That's 6.37 millimeters, which is roughly the width of the M that I've got here. So this proton doesn't penetrate very far into that electric field. There's an easier way to do this problem, and I want to show you that. I didn't write down the third of our constant acceleration equation, so I'm going to do that now. The third equation is this. It's v squared minus v naught squared equals 2a delta x. Now, here's what I know in this equation. I know the acceleration, I know v naught, and I know that when it comes to rest, v is going to be 0. So this equation changes into minus v naught squared equals 2a delta x, or delta x is equal to minus v naught squared over 2a. And we have the same v naught and a from before. V naught is equal to 5.45 times 10 to the 5th meters per second. The acceleration is still negative, it's slowing down, minus 2.33 times 10 to the 13th meters per second squared. I can plug those numbers in here. Delta x equals minus that number, 5.45 times 10 to the 5th meters per second squared. And on the bottom is 2 times that minus 2.33 times 10 to the 13th meters per second squared. Unit-wise, I know I'll have meters squared per second squared on top, because that gets squared. On the bottom, I have meters per second squared, and I'll end up with meters for my units. Let's see what it comes out to be. Well, amazingly enough, I get 6.37 millimeters again. Actually comes out 6.37 times 10 to the minus 3rd meters. The minus signs divide out on there, top and bottom. So I get the same answer. This was a much easier way to do it than the other way. So when you're solving problems, keep your eyes open. Sometimes you can save yourself a bit of work by using a more appropriate equation.